In trying to figure out a theory of quantum gravity, we have to obviously confront the notion that gravitational fields are composed of quanta. If they're not composed of quanta at all, then there's no such thing as quantum gravity. There's no need to quantize gravity, and yeah, there's just these smooth continua that go all the way down to the quantum realm, as in general relativity. And general relativity turns out to be a fundamental theory in physics rather than something that is based upon the spookier aspects of physics, there's quantum mechanical stuff going on at a very fundamental level, but it seems contradicted by quantum mechanics. General relativity does. It seems incompatible, let's say, with general relativity, because we have certain very well-tested phenomena that we know of in quantum theory, such as this idea of quantum entanglement, which is incredibly well studied, this so-called spooky action at a distance. We find violations of this perfect limit of light speed transmission of information in general relativity, which is an extension, of course, of classical physics. And what we find is, particles moving faster than light, for instance. So we need some sort of way of negotiating that with the picture of general relativity. It is not at all obvious how this general relativity space-time substance is going to allow particles to travel faster than light. You know, why does the substance itself, this mysterious bending, squeezing, squishing, trampoline-like four-dimensional surface, why does it give off radiation according to the cosmological constant? Why does it allow particles to tunnel within it faster than the speed of light? It doesn't make a huge amount of sense, I have to say. However, I think that the better way of looking at things is still from actually a quantum mechanical perspective, and trying to figure out how we can use the particles of the standard model that we know of already, or how we can use ensembles of standard model particles to predict the various interactions and behaviours that could, in principle at least, be associated with gravitational phenomena at the macroscopic scale. So we say that nature is permeated by fields. We have the electrical field, the magnetic field, which go together to form obviously the electromagnetic field. Then we have the neutrino field, the quark field, if you like, of which quarks, electrons, neutrinos, etc., are manifestations, are the individuated base units of those fields. So really, like, what a field is just a collection of particles. It's a collection of particles moving through space and interacting with other particles. And we live in this kind of cosmic soup of particles, whereby order, structure, and the various other things that we associate with the low energy universe that we inhabit of everyday reality, where these phenomena are allowed to exist, such as the formation and maintenance of atomic structure, for example, which forms the basis of basically every other structure built upon it. We can see that really as being a kind of a basic interaction between electrons and protons, more or less, with neutrons tacked on in the nucleus as kind of extra baggage that the nucleus has, really. And it's an interesting question as to, frankly, why neutrons stay in the nucleus at all. They must be staying there to some extent because of the electrostatic forces of the nucleus, to some extent because of the nucleus's charge. And I'm going to talk at length about neutrons and beta decay in this video, hopefully, because it's been one of the major wrinkles in my theory of quantum gravity. It's been one of the things I've had to invoke a pretty bullshitty notion, or a pretty bullshit sounding notion, to try and navigate my way around. But nonetheless, it presents interesting possibilities, and when thinking about the physics of neutrons in the nucleus, I think we can approach a better understanding of how neutrons behave outside the nucleus. So neutrons are are bound within the nucleus for some reason. This is, I would imagine, because of the electrostatic forces between the quarks in the neutrons, between, I believe, tunneling background electrons, which form the gravitational field. There's this very ephemeral, very attenuated form of electromagnetism that basically gives rise to the force of gravity as we understand it, that permeates all of reality and provides a slight pulling force to objects falling into such a cloud. And yeah, so when it comes to neutrons in the nucleus, we find on the one hand that the positive charge of the up, well, it's better to see a nucleus in a different way, I think. It's rather arbitrary, is it not, to see the nucleus as sort of protons and neutrons, and it's a bundle of protons and neutrons sort of oscillating and exchanging particles and absorbing energy and doing all the stuff that nuclei do. It's probably better to look at it just as like a soup of quarks, really, jumbled up, but like buzzing around, and yeah, it's not really like distinguished into protons and neutrons so much in the nucleus. It's more like it's a bundle of quarks which en masse has a positive charge, and that positive charge is balanced out by the negative charge of the electron, and the electron is indeed bound to the nucleus because electrons constantly exchange, frankly, W particles, in my opinion, with the nucleus. Whenever an electron gets into the electroweak range of the nucleus, this area of positive charge, they exchange W particles. While the W particles are being exchanged, my opinion is that the mutual charge between the W plus and W minus, which is simultaneously exchanged, cancels out the charge, leaving it chargeless. It also cancels out the masses of the W particles and leaving them indistinguishable from photons and causing it to be a massless spin-2 gauge field of a composite variety, if you see what I mean. And this is really what we've come to call the graviton, or this is what the graviton is predicted to be. So I'm going to talk a bit more about neutrons in due course, probably just after this explanation of my own approach to quantum gravity, which is that I believe that far from what we expected prior to the second quantum revolution, an electron can actually really be anywhere in the universe. So we find electrons popping up very briefly for perhaps a Planck time before it again is measured by a background photon, or usually a photon, and gains some momentum, has a great measurement taken over its position, and its momentum accelerates faster than light, and it tunnels to somewhere else in the universe. That electron is then replaced by yet another electron from somewhere else in the universe, and so on and so forth. And yeah, then this new electron interacts with something again almost immediately, disappears again, to be replaced by another electron, and so on and so on. And that's the principle of non-locality acting on these systems, that what this second quantum revolution has revealed. That each time we observe an electron in space and then another one pops up soon after it, we have no good reason to expect that new electron to be the same electron as the electron that disappeared, if you see what I mean. So very, very spooky, very, very mind-bending, out there stuff, it really is. But you know, nonetheless, this is the physics that seems to be the case. So it's really rather amazing, in my opinion. But yeah, to go back to neutrons, so like one problem I've encountered, and one problem which I've come up with various attempts at solutions for, is why is it the case that neutrons fall to Earth like a rock when they're in their free state prior to beta decay? Neutrons decay after about 15 minutes or so. During that time, they are under the influence of gravity. They fall, you know, like a stone would, or like a tennis ball would. They follow a curved trajectory towards the mass. The answer I came up with to that is not very good, I don't think, in my opinion. But my idea for gravity has so much utility, I think, that I can't quite abandon it just for a slight inconsistency like that. So what I believe happens is that the up quark of the neutron gets flipped down towards the area of the gravitational field where there's the highest density of electrons. So it gets pointed towards an area where it's most attracted to, where it most wants to be. Most wants to be near this big, cloud of negatively charged particles. The protons have less influence over the neutron because the protons are all bound up within atoms. So actually the particles that have the closest proximity to the neutron are in fact these background electrons that I describe, and these influence and these have provide more force over the neutron than the protons do. So and then what it does also is it starts to spin, and this spin prevents its two down quarks, both of which have -1/3 charge, from being able to resist the gravitational field to the extent that the neutron would just sort of float around, if you see what I mean. It sort of attenuates that force of resistance there to a great enough extent, allowing the neutron just to fall guided by its up quark with positive 2/3 charge towards the negatively charged electrons as it gets closer to the ground. If you were to fire it out of a neutrino, a neutron beam generator, for example, and that's roughly how I think that would work. So I think what we would need to do is model that with computers and things to sort of try and prove it, if at all possible, or to provide some more evidence that it is indeed the truth. I still believe that largely because of the ways in which these background electron fields would be interacting with particles of light, I think it makes it sit very neatly with general relativity. I think we can gain some great new insight as to how dark matter behaves, and we can take into account, for instance, the resistance generated between bodies in light of their rotations and things. If the electron densities associated with each body, if each body's gravitational field is indeed a cloud of electrons, then the rotation of those bodies will be causing resistance within the system and prevent them being so easily shifted upon their orbits. And you can see how that might lead to the galactic rotation curves that we see. These objects like traveling more slowly closer to the centers of the galaxy, as opposed to objects moving faster at the extremities of galaxies, because there's simply like a greater and greater amount of background electrons they need to move through. That's causing their orbital velocities to slow down. I think it has a great deal of utility in a great many ways in terms of explaining phenomena in physics that we observe. So, back to neutrons, possibly. I think that the way that they behave in nuclei, the reason why they stay in nuclei is not obvious. If they're merely negatively charged particles, there's no especially good reason why they wouldn't merely just fall out of the nucleus like a neutrino would if they're negatively charged. So I think we can conjecture on the basis of that, on the basis that there's some background force there operating which causes them to maintain maintain a presence within nuclei without merely just getting emitted straight away. And because if we're going to say that electrons and protons have no influence over keeping neutrons in the nucleus, then And then we would have to say that, if you see what I mean, then we would have to say, during the transit through space, they would travel in straight lines and not be affected by background electron density. But because they're bound within nuclei, I think because of something other than colour charge, which I don't quite agree with. I agree sort of more that there's a residual. I mean, they call it the residual strong interaction, mediated by kaons and pions and things, and that's one way of looking at it. But I'm just wondering, like, where those particles are ultimately coming from, if not actually from the background itself, and and they're obviously coming from. I mean, the pions are coming from protons, aren't they? So I think what we can at least conjecture on the basis of that is that there is some extent to which the neutron can be influenced by electrostatics, since obviously a pion or a kaon is an electrostatic particle, and that ultimately makes the strong force, the residual strong force anyway, electrostatic in character. So it carries with it the implication that electrostatics are able to influence the behaviours of neutrons when they're at large as free particles. So I think actually addressing this neutron problem in quantum gravity, in my idea of quantum gravity, I don't think it's so ridiculous anymore. Actually, I think it's less problematic than perhaps a lot of people would like to suspect it is. I've dealt also with this issue of the exponential functions governing electron wave functions and saying, oh no, they can't tunnel that far, and saying, like, well, because of non-local realism, like, you don't even know when an electron tunnels across a potential barrier whether or not it's the same electron actually appearing across the potential barrier, but all you know is it's just a different electron from a different part of the universe. So that's the world we're living in, ladies and gentlemen. The state of physics in the year 2026. Fascinating times, but nonetheless, still problems we have to overcome, I think. And that's what I wanted to say. So the video mostly about neutrons, but quantum gravity more generally, and see you on the flip side.